share my screen and start the presentation.
Right, sir.
So I hope the screen is visible to everybody. I will talk about a topic which is a topic of great importance in the modern era. It concerns medical diagnostics with blood. Now, if you consider medical diagnostics with blood, it is something which very commonly one has to undergo. Typically in the modern healthcare scenario, where doctors do not come up with any kind of recommendation without certain basic diagnostic tests. However, the other side of the picture is very dismal. Majority of the population who live in a country like ours is deprived of basic healthcare amenities and facilities. As such, only around 25% of the population who live in urban areas, including big cities, enjoy the access to about 2/3 of the India's hospital beds. This maldistribution creates lots and lots of issues, and healthcare ecosystem often comes to a collapse. As people, we always complain about various shortages, like shortages of doctors, nurses, technicians, barriers to access, etc. But we often forget about the role of technology, in a sense that the conventional technologies which work very nicely in the lab may not work so well outside controlled lab settings. But certain technologies which are lab based need to be made available in some form or the other for common people, where there is extreme need of detecting various ailments. For example, if you think of anemia, in India, about 58.6% of children and 50% of pregnant women, they are found to be anemic. In underserved areas, this never gets detected because of the lack of infrastructure. To overcome these barriers, there has been a recent upsurge of efforts to build up certain facilities known as health kiosks in villages. In these kiosks, the patient approaches the frontline health worker, who is typically a minimally trained boy or girl, and shares with that person the various health issues and discomforts. Some of these are input in a medical algorithm driven software, and the input data as well as other relevant information is transferred to a doctor who is sitting in the big city via telemedicine. The doctor who is sitting in the big city makes a consultation with the patient over telephone if additional consultation is required, and then comes up with a recommendation. So far, this works beautifully because these frontline health workers, they undergo a proper training system. The software is reasonably advanced. Internet connectivity in villages is quite good nowadays. But the problem comes when the doctor gives a recommendation. Invariably, the recommendation includes some diagnostic test and mostly the very basic ones to begin with. But even either those are too expensive, or leaving apart the cost, the infrastructure for undertaking those tests may not be there at all. There are other more technical issues. For example, the reagents which are very commonly used for testing with blood and other body fluid samples, these reagents may not themselves be stable under such difficult conditions. All in all, it requires some major innovations in diagnostics. While making the technological innovation, one has to keep in mind that the power supply is not so nice and stable in most of the rural scenarios. The environment is hot, dusty, humid. The storage of reagents is not possible in the manner in which we do in the lab because of the lack of controlled lab environment, including the requisite controlled air conditioners and refrigerators. The supply chain of these devices or these materials which are necessary for doing this diagnostic work, that doesn't exist. Skilled technicians are not commonly available, and price wise or cost wise it is so sensitive that it may be prohibitive to do the test. As a remedy to this, it may alternatively be possible to imagine a paradigm in which one can do diagnostics with one drop of body fluid, for example blood, at the point of care. What it means is that the patient doesn't have to travel to the hospital, but instead you prick the finger of the patient with a proper finger pricking needle which is available. Then one drop of blood is taken from there and loaded in the device, which in this case is a strip of paper. The paper has embedded reagents at certain places. The blood will react with the reagent and have a colorimetric change. That color, whatever is the color signal, that is transformed into a digital output, and then there is a calibration that is done. If we have known blood samples, we know what is the, for example, what is the blood sugar or hemoglobin or whatever, and so we make a calibration chart of that against the intensity of the color image. In that way, using that calibration curve for unknown samples, that is for samples for which the result is not known, we can predict the value, that is the glucose, hemoglobin, some parameter. These are highly portable units with on-spot diagnostics possible, functional with limited resources, easy to handle, their mass manufacturing is possible, inexpensive, they require minimum infrastructure, they are rapid and easy to monitor and can be automated. Now, how do we make these devices work? In the previous slide, you all have seen a strip of paper. So we can start with a piece of paper and make certain designs on the piece of paper to make it effectively a diagnostic strip. So what I will show you is that with a clear imagination, using a paper, pencil and eraser, which are common classroom, kids' classroom materials, one can convert them into diagnostic devices. Now, in these diagnostic devices, imagine that you have a paper strip. Paper has numerous small pores. So, in each of these pores, if we have a liquid that is moving, and it is moving with no acceleration, that is, it is moving as a in equilibrium, in local equilibrium with the sum total of the forces as 0. Then the surface tension, gravity and viscous force, some algebraic sum of them is equal to 0. Now, if we substitute expressions for those forces and try to get an analytical solution with certain assumptions, the most important finding that we get is that when gravity force is not there, if you make a balance between the viscous force and the surface tension, this is a surface tension force, capital H is the static height or capillary rise. If you separate the variables, you get the instantaneous displacement in the capillary is proportional to square root of time. That means the time required to completely fill up a pore in paper can in principle be assessed by the simple law. But reality is much more complicated than this. Paper is not a simple porous medium. It is a tortuous random network of cellulose fibers. So the model, the theory that I have shown thus far is perhaps too simple to capture how a liquid spreads on paper. But interestingly, if we make a statistical averaging of the spreading phenomenon all around the paper, then it comes down to a sort of a diffusive law or diffusion law, where A square is equal to some effective diffusion coefficient times the time. When blood flows through such paper pores, complications are much more. The reason is the blood has red blood cells. Of course, it has also other cells, but the red blood cells are the largest in size and largest in number. They are largest in number. And what they do normally is they try to block certain locations in the pores so that the remaining blood, that is the plasma of the blood, will find a pathway that is not normally as simple as a straight channel or a straight tube. This kind of movement is even more interesting if you have the capillary already pre-saturated with glycerol, say another fluid, and the blood displaces that and undergoes a capillary dynamics. These are extreme complex problems in physics, but in a paper matrix this commonly happens. In a real paper, a greater challenge, which so far not many people have addressed, is that the paper is having its own deformability, including the swelling and getting wet and disintegrating. So that gives rise to certain additional forces which are very, very difficult to account theoretically. And that means the pore scale mechanics in paper is itself an extremely complex scenario. If you see the experiment that is going on in the bottom right corner of this slide, so after finger pricking, one drop of blood is spread on a glycerol soaked paper and certain patterns are formed. Well, this could also be used for disease diagnostics, but to make this a diagnostic platform, it is better not to allow the paper to spread, allow the blood to spread randomly, but to be constrained to move in a way that it reaches a destination where certain reagents are there. And in principle, the blood can react with the reagent to change the color. So now to direct the blood from the source to the destination, you cannot do it by having a random paper strip. So what you require is a directed motion of blood. So these black regions you require as hydrophobic barriers, which will not allow the blood to flow in a cross direction. And in the longitudinal direction, if this channel is small in size, that means small in diameter, then by capillary action itself, the blood can move from one end to the other. Now this kind of simple concept of hydrophobic barrier, we translated in the form of a technology that can print microchannels on. You do not require any specialized lab resources to do this. What you require is a design made possibly like this, printing the same design on both sides of the paper and then heating the same for around 4 to 5 minutes at 200 degrees centigrade. In that way, the toner particles which come from the printer that will melt and block these pores in the black region. So it will be a leakage tight hydrophobic barrier. That means your paper microchannel is melt. So by a very simple process, it is possible to come up with a diagnostic technology based on this, where by integrating the same with the smartphone, you get a prediction of the corresponding blood analyte concentration. So for example, if you see here that you have a paper channel where the blood is collected and there is a membrane which separates the plasma from the whole blood, and the plasma goes by surface tension action, goes to the reagent channel where you have glucose oxidase, peroxidase, etc. for glucose. Blood will react with that blood plasma here and have a reddish brown color, and the intensity of that is mapped with the grayscale intensity, and accordingly you can prepare a nice calibration. You can also make hydrophobic barriers by simply depositing the whitener ink that we commonly use to whiten the ink marks on paper. So the whitener ink contains various materials which make them amenable for hydrophobic mediums. Proceeding in a similar manner, we could also do hemoglobin tests, and that also in a range of as low as around 2 to 2.5, where it is a dangerously low hemoglobin level and it can actually give rise to fatal conditions. Well, microfluidics is such a subject that the advancement is never ending. When capillary action was sufficient to drive the flow, then what happens is that one can use other field effects. For example, one can use electric field to drive the flow. In that way, the blood can move faster from the source to the destination. But for that you require to make electrodes. Depositing electrodes in micro and nano devices is a hell of a job. Requires cost, sophistication, complexity, etc. What we did is a very simple thing instead, which even a school child can do. So we deposited the paper with pencil sketched electrodes. So basically these square regions are pencil sketched marks. The graphite in the tip of the lead, it acts as an electrode and facilitates the entire procedure of electrode deposition in such a simple way. Using this technology, we could do multiple tests with single drop of blood. So on one branch we are doing here glucose concentration evaluation, and another is hemoglobin, bilirubin, which is a very important liver function. Now, the methods which we have seen so far are quite promising, but one of the big challenges is they still require reagents, chemical reagents to do the test. As I mentioned earlier, there is a very weak supply chain of reagents in remote areas. They are costly and they cannot be stored at extremely controlled conditions. So the question is that can the rheology and the fluid dynamics of blood be used for such purposes? So if you see the constitution of blood, it has red blood cells, white blood cells and platelets. The red blood cells are very, very important cellular components which effectively determine the nature of the blood flow. Normally these cells are biconcave discs, but under shear they can deform and they modulate the flow in an extremely critical manner. Other cells like WBC and platelets are still important, but not to an extent that those could very importantly alter the flow. Now, one can develop some theoretical insight by noting the behavior of blood at high shear rate and low shear rate. At very low shear rate, the red blood cells form aggregates. Whereas if you increase the shear rate, these aggregate entities will be sheared off and the blood will flow better. So this is called as a shear thinning nature of blood. Now what controls this behavior of blood? Essentially the hematocrit, which is the volume fraction of the red blood cells. So what you see here is that the red blood cells have an extremely critical impact in terms of creating a shape change, shape deformation in a microfluidic channel. Now these blood cells which are invading the channel, if there is no external force, the blood moves by diffusion. What happens in paper is that the diffusion is not uniform. It is random because the entire phenomenon of blocking the paper pores by the red blood cell, it is we try to ensure that it is addressed, but it all leads to extreme complications. So this is something, a very simple experiment which could be done with blood on a paper. So when the paper is soaked with glycerol and blood with different hematocrit levels is dispensed on that, then the blood will spread. If you see these examples which are done with blood samples of 5 different hematocrit values. Very interestingly, we tried to compare the spreading radius of blood as a function of time for the blood plasma, which is this black curve, whole blood with different hematocrit concentrations, all clustered in the red line, and simple water. So what we can see is the plasma, although its water is different from water, and the blood is further different from plasma and water, and the difference is not so much at different hematocrit levels. However, blood clearly does not spread in the same manner as water and plasma. So what we could figure out is something very interesting, that if the hematocrit of the blood is altered, say from 30 to 50%, the radial spread of the blood sample, that doesn't change perceptibly. Now, This happens because the red blood cells, even with a threshold concentration, they are able to block the paper pores. It is very similar to how maybe polystyrene particles block the pores, and we can see that with the paper matrices taken by us with different particle concentrations, the average pore blockage is about 50% of the original pore without blockage. In each of these pores, as I told you, that we can apply the balance of surface tension and viscous force, and you can use a new non-Newtonian law, power law, to calculate the wall shear stress. The power law indices K and N for blood will depend on the coefficient C3, C1. These are patient specific coefficients, and very importantly the hematocrit level H. So in this way, we put forward a theory which is trained by experimental data to an extent that we figured out that the average radius of spreading is about 50% of that as predicted by the theory. Now what happens if blood is displacing another fluid of higher viscosity? For example, blood displacing glycerol in a porous medium. Then what is commonly seen is a kind of beautiful finger-like pattern or projection, which in fluid mechanics is known as fingering instability. So the competition between surface tension and viscous force dictates this instability, and that is dictated by the capillary number, which is the viscous to surface tension force. But this is important only if the fluids are immiscible. But if they are miscible, it is dictated by a critical Peclet number, which is the ratio of the convection to diffusion. Beyond the critical Peclet number, the flow is so strong that this competition of forces, it will be difficult to ascertain. So what you can see here is that if you have a drop of blood and it spreads at different hematocrit levels, it spreads differently, and it is possible to utilize this the finger-like projection. What you see here is not only a strong function of the hematocrit, but also implicitly on the particle concentration. That means the red blood cell concentration. To understand that, what we try to do is to infuse a few particles of around 20 micron in size, and you can clearly see how it spreads under such conditions. So all in all, what we could do is we could figure out the essential outcome of the different styles of spreading of blood at different hematocrit levels in the form of a diagnostic technology where no chemical is required for the testing. So what we found is that as the hematocrit level increases, the blood viscosity increases, which decreases a parameter known as the log mobility ratio, and this attenuates the fingering instability at higher hematocrit concentration. Now, what we wanted to do is not just to have such a technology where by observing the spreading of blood we could predict one of the very important blood parameters, but to convert it into an image analysis or image processing algorithm which could be in principle integrated with a smartphone. So we calculated the fractal dimension of the pattern, and again we could clearly see a band between one aqueous dye, then blood with hematocrit 20%, and the blood with other hematocrit levels. So if you plot the fractal dimension versus hematocrit, it's a nice, almost like a rectangular hyperbola curve, and from that we can clearly figure out what is the corresponding hematocrit level for a given fractal dimension, and that is your test result. So summarily, what we do here is to observe the blood spreading on the paper, which is pre-soaked with glycerol, analyze the patterned structure of the blood that is formed over time during this experiment, and then find out the fractal dimension of the pattern and convert that into a calibration based on the hematocrit level. In this way, it is possible to classify the dangerously low, moderately low, or normal level of hemoglobin or hematocrit. Now, paper is of course a platform which is very commonly used. It is simple and user friendly. Cost is very less. But the problem with this paper is that paper swells and disintegrates very easily when brought in contact with the liquid. So what we wanted to see is that instead of paper, can we use the fabric or the cloth? So from lab on a paper to lab on a cloth. Cloth is an elusively simple platform. If you use cloth, the advantage is that these have good weight strength, biocompatible, and very importantly, you can convert these into wearable sensors. And liquid spreading on cloth has a lot of resemblance with liquid spreading on paper. Again, the channels that can be made on cloth for this purpose will either be expensive or time consuming, or they will require skilled technicians. So this is an example where one of my students worked on handicraft inspired fabrication of lab on cloth. So one piece of cloth and then making hydrophobic barriers on that by using a wood finish, linseed oil and mineral spirit. So this is just like a handicraft and can be done. These hydrophobic barriers, once they are made, and you can clearly see that the channels which are there in the cloth, the hydrophobic barriers which are in the surroundings, they are so effective that they are not allowing the blood to cross flow. The blood is just flowing as it is. So this means that the fabric or the cloth has great promises for such technologies. It was further confirmed by making channels of different shapes for mixing or diagnostic purposes. We found that the hydrophobic barrier, the formula that we have put in, it is extremely stable and it cannot be disintegrated by blood, urine, saliva, HCl, glycerol, DMSO, PBS, etc. So we could successfully do blood glucose estimation on cloth with the highest data, about more than 500 milligram per deciliter blood glucose. That also could be detected quite successfully. So now these sensors, these cloth-based sensors, are very promising. As I told you, that these can be integrated with smartphone analysis to develop the sweat-based wearables. At point of care, typically electrolyte, glucose, pH, etc. So these platforms can be fabricated rapidly, virtually equipment free. The painting liquid is made from common household materials. The diagnostic device is of low cost, it doesn't require any skilled human resources. And the reproducibility is very, very high. Because the manufacturing is quite simple, it can be upscaled to impact the rural livelihood via another handicraft revolution. It is possible that with this kind of activities, mass employment opportunities in rural sectors can be there. So from a rural handicraft, an organized effort could give rise to a step which is socio-economically beneficial, a step for self-reliant India to work on diagnostic technologies in a completely indigenous rural ecosystem. The cloth offers further interesting facets. In one of our independent studies, we showed that if such clothes are mounted outside for drying in a solar ambience, the streaming potential that is generated there is able to light a white LED lamp. Such power, though low power, are extremely important in terms of running the medical sensors. So all these, either paper or cloth, they can lead us to a paradigm of reagent-free method for disease detection. The entire thing can be integrated with the smartphone. These are functional even in poor infrastructure without trained personnel can be implemented either in primary health centers or at other places as point of care tests, and can be also used as a life-saving decision-making tool in case the level of, say, hemoglobin has come down to a very, very critical limit. So all in all, it can create not just an impact in diagnostic technology, but also an impact in terms of the socio-economic well-being of the underserved community, typically the rural community. I would like to thank all my colleagues, present students, former students, and various funding agencies who at different points of time have funded generously to enable us working on these extremely difficult problems, which hold the potential of reaching the grassroots level and impacting the last mile of the population. I will wind up with a demonstration movie here. This is a rural healthcare center where our team had visited to do some basic diagnostic tests. This is a location in a place called as Barra in district Birbhum, West Bengal. Frontline health workers were engaged in doing diagnostic tests using the technologies which have been developed by us, and in parallel other forms of point of care diagnostic devices which exist in a commercial basis, like HemoQ, for example, is a disease detection platform for hemoglobin levels. So all in all, we could come to a situation where just by a simple strip of paper interfaced with a smartphone exactly in the same way as a credit card reader reads a credit card, it was possible for us to make diagnostic predictions, in this case for blood glucose and hemoglobin, which are extremely accurate and could hold the potential of changing the lives of millions of people. So thank you all very much for listening to this talk, and we may address a few questions or comments.
Thank you very much, sir, for this. First time I knew that a mechanical engineer also contribute for the society in this manner. So thank you for addressing our audience. So I request now, Pratham, please read question one by one.
Okay, sir. So one question is that since the starting we discussed the experiments on papers, was there any specific type of paper that was used for this experiment and why?
Yes. So these are known as Whatman filter papers. So there are different grades of Whatman filter papers. So these filter papers are the particular types of papers where the pore size distribution, it has an average dimension. For example, this Whatman 4 filter paper, which is very commonly used, has an average pore dimension of about 11 micron. So in this way, different grades of papers are there, and we use those filter papers for the experiments.
So the next question is, what is the approximate manufacturing cost of this particular product?
So manufacturing cost means you have this portable electronic readout box. So it could be say around 2,000 rupees per box, but it is a fixed equipment, so you don't have to really buy it more than once. The smartphone is yours, so I am not taking it as a part of the cost. And per test, you need to have a strip with 1 drop of certain reagents. So about 1 to 2 rupees per test for glucose and hemoglobin.
Another question is, how microfluidic reactions are controlled? If one fluid is acting as a petri dish for other fluids, how do we make sure that a particular amount of droplets go into the other fluid?
First of all, so while dispensing the droplet, we have a preset pipette dispensing. So if the pipette is pressed, automatically that amount of microliter of blood is dispensed, and in the reaction pad, whatever is the proportionate volume of the reagents, those reagents are already there. So that means we already work out a stoichiometric ratio, and accordingly we supply the blood, and the chemical reagent is also embedded with that stoichiometric proportion.
And one more question is there. Can we use the redness of the blood stain on paper as a parameter to determine RBC quantity in blood?
Yes, I mean, to some extent it can be done, but redness actually, I mean, sometimes it masks out certain various factors for which redness could be there. For example, I will tell you a very simple thing. Once we were discussing about this technology, then one rural doctor said that I do not require any technology for hemoglobin detection, because I just open the eyelids of a patient, and if the eyelids are sufficiently reddish or pinkish, I say that the hemoglobin is sufficient, and if it is whitish or pale, that means hemoglobin is low. And now, I mean, there is a different, just on a lighter note, there are many people who are intoxicated and their eye is absolutely red. I mean, you open the eyelash and it will be almost a dark red color. Now these are certain artifacts. That color artifact could come out of many things. For example, if you have a red color of your say face has become suddenly red, it could become many things. I mean, it could mean many things. So these are not specific. So the test that what we are doing is specific because it is related to a reaction that directly involves that particular analyte, glucose, hemoglobin, etc., and not something which is an indirect observation. That indirect observation may be correct, but it also has a chance of being incorrect because of not being specific.
Sir, I have a question. Suppose, sir, in a single gadget, is it possible to get multiple testing result? Because we are means majority we are afraid about piercing injection in many times.
No, that is what it is. The entire objective is that if you have 1 drop of blood, I showed one example where with 1 drop of blood you can do simultaneously say glucose and bilirubin. So that is one illustrative example, but in principle, several tests of that kind can actually be done. So it is possible to do multiple tests with a single drop of water. That is possible.
Okay. Sir, can you suggest some area where our means BTech project or MTech project or PhD student project we can give this kind of means project and
No, I
what
think
are
these are even these are so simple actually. You can give these as school projects also. See what is required. You require a piece of paper in which by MS Word you can make this design. Just print it not on a regular paper but a type of filter paper that can be purchased. It's a simple thing to purchase. And after the printing, you just get hold of a hot plate, which is very commonly available. Even in one can use the hot plate of the micro oven also to heat it. So at a particular temperature, and then the paper micro channel is prepared. Now, initially, one should not try to do experiments with blood. I would say mechanical engineering. One of the building blocks of mechanical engineering is fluid mechanics. So
Right.
one can study the basic of fluid mechanics as a blood-like fluid flows through these channels by capillary action. So instead of blood, because handling with blood has certain issues and it is not always necessary until and unless somebody is doing a medical test to handle blood. But one can handle some blood analog fluids. These are available, synthetic fluids, which have their apparent viscosity like blood, although they are not physically blood. So those fluids can be used, and one can actually study, for example, what is the time required to fill up the channel, or what is the time required to complete a reaction. When a color is developed, how it is imaged, like a smartphone camera can be used to take the image, do the image analysis, how the calibration is done. All those things can be done with simple engineering sense, without actually referring to blood as a biological fluid.
right, sir, correct. Sir, I have seen in your presentation one equipment same. It is also available here. Same XRD we can do here. Sir, what are the basic others equipment that we can purchase and we can give this kind of project at higher level, means for master or PhD, so that some means output definitely comes for the society.
Masters and PhD level, what is required is basic characterization. So basic characterization means one is like this material or surface characterization, which is SEM, TEM, AFM, like that. Then for these kind of experiments, you also may require certain visualization. So which is typically high-speed camera and microscope. So if you have this and to measure certain properties on the surface, say contact angle, you may require a goniometer. And to measure, say, the film thickness on surface, you may require something called as ellipsometer. So these are, more than sufficient actually to develop the characterization facility for this.
Okay, sir. Okay. Thank you, Putham. Sir have given sufficient time. One or two questions, okay, maximum.
Yes, sir. Sir, were these results obtained by the use of images taken by common DSLR cameras? Will different results will be obtained with the use of infrared cameras?
No, infrared camera is not necessary for these. These are all results obtained using a particular smartphone camera.
Okay. Sir, one last question, sir. Sir, what are flow control systems for microfluidics?
So flow control systems can be, say, you can use electric field, you can use capillary valving, you can use even a pressure-driven flow like a syringe, injection syringe, which is called a syringe pump in microfluidics. You can use the rotation, the centrifugal force. You can use acoustics. So there are different ways in which you can control the flow. Here, the flow control is by surface tension in these examples.
Okay, sir.
Sir, thank you very much. I'm really very much thankful to you that from your busy schedule you have given time. And sir, I request in future also you can share your knowledge with our student. And After this pandemic, I hope if online courses will conduct, you definitely come and address our students. Thank you very much, sir. I'm very much thankful to you again.
Thank you very much. It was a pleasure, and great to see so many young students participating. They are all our future, so to say. They are going to take over everything. So all the best. NIT Hamidpur is doing wonderfully well. And,
Thank you very much, Mr. Chakravarti. Being a encouraging part, I literally extend my gratitude to you for sparing the students of NIT. Although number of students we in pretty good, but certainly interaction with all the students was literally the demand of time, just in a meaningful manner. So thank you very much. And I hope that in future also NIT Hamidpur's association will bring a good result for the institute as well as for the students. Thank you very much.
thank you very much. Thank you very much, all, and all the best for all your subsequent endeavors. Stay safe. Now it's again another round of challenge to our nation has come because of the new wave of the coronavirus. So let us all hope for the best.
Right, sir. Correct. Thank you, sir. Thank you very much again. Okay, Pratham. I hope all of you, all the participants, enjoy this session. It's a really first time I realize that one means the people having the background of mechanical engineering can do this kind of work. So today I have enriched very much about the knowledge and experience shared by Professor uh, Suman Chakravarti, and I think our HOD just joined and give a thanking message to Professor Chakravarti. So thanking you again. I think our HOD left this session. No problem. 26th, we have another lecture, last lecture, will be given by Ms. Apurva Jakadi. And this is my very, very kind request to you. You please stay present. Otherwise, from the department and NIT, it is giving a bad message to the expert that our students are not interested to listen this kind of expert talk, and even maybe the authority will not allow us to organize this kind of courses or activities. So this is my request. Really, I'm requesting you from my heart. I'm requesting you. Please encourage your friend to join if they feel this lecture is boring or not suiting him or her. Please say stay tuned, but you can leave. Okay, just log in yourself, and we are not seeing your face, so your present is not shown to us. So please stay with them, and I request all the seer of different year, they have the responsibility to convince 30 to 40 students at least to join this kind of event, because as a seer you are the head of this is year, so you must have the convincing power to bring at least 30 to 40 students. With this all good wishes, I hope you enjoy this session. All the best. If you want to share something with me, you can share. Pratham, one thing today you miss it, that is to read the biosketch, and that first day we have some means inauguration function type things we organize, that where the YC of that particular